welcome back to Info Index. Today we're going to be talking about some prerequisites to the electrodynamics, Introduction to Electrodynamics course that I'll be covering on this channel. So I'm going to assume that you all have taken the default high school classes, so like, you know, basic calculus and all that physics stuff. So first, I assume you already know what ordinary derivative is, right? So ordinary derivative is just, say you have a function fx, ordinary derivative will just be df over dx, right? This basically tells you if you have a graph of fx, say it looks like this, how a change in the x direction affects the change in the y direction. This basically tells you that, right? So now I want to apply this to the 3 dimensions. So say you have a pool of water, and it has varying depths, and the depth function is 3 variables, right, in x, y, and z direction. Well, actually it's 2 variables in the x and y direction. Let's just call it 2 variables. So f, x, and y, right? So now if you want to find how the depth changes as they move in the xy plane, then you're going to have to take the gradient of that, right? And the gradient is going to be what we're talking about first. So the gradient is basically, well, if you want to find a change, right? So the gradient is going to be the gradient. I'm going to not write gradient because I can't write on this. All right, so the gradient is basically going to be your partial f. Don't worry, I'll talk about this later. Partial f, partial x in the dx direction, plus your partial f, partial y in the dy direction. So basically this is talking about, this is partial f, partial x, right? So say this is the x direction, this is the y direction. It's how much the depth changes as you move in this direction. And dx is infinitesimal amount, right? So how much the depth changes if you move an infinitesimal amount in this direction, and how much the depth changes if you move an infinitesimal amount in the y direction, which is this term right here. So this tells you the gradient, right? And the gradient, this can be seen as a dot product if you have partial f, partial x in the x direction, plus partial f, partial y in the y direction. And you dot this with your infinitesimal change in x direction plus your dy in the y direction. Find these two are the same thing, right? Because the vector dot products, right? So now this thing here is your gradient, and this thing here is your length element, dl. So this can be represented as dl. Talk about this later. And this here is going to be a gradient of f. So the way you write gradient is just upside down triangle and f. Well, I can write xy to make sure that you're not confusing this f with this f. Right, so this is your gradient. I'm going to try my best to write the words. This is your gradient. Ah yes, quality handwriting. Now the next thing we're going to be talking about is the divergence of this function. So say there's a current in this body of water. So let's draw a vector field for the flow of currents on this body of water. So let's say at one point it's all going inwards, right? Another point it's all flowing away from the point. So here at this point, you can think of this as a negative divergence because everything's flowing towards it, right? So it's negative divergence. And this point, vice versa, everything's flowing away from this point, so you can call it positive divergence. And what you think about this is, a negative divergence can be seen as the point as a drain, because all the water is going towards it, and it has to disappear here, right? So there's a drain here. And the positive divergence can be thought about as a faucet, because water is coming out here, right? Because no water is going in. There's more coming out than going in. So it has to be a faucet or a water source. And the way you calculate divergence is basically take the upside down triangle and dot it with your function, right? You can just tell this as this is a Nabla operator, right? A Nabla operator. We define this as being a vector with the number of, just basically made of partials. And the number of partials depending on the number of dimensions or variables that your function you're dotting it or applying it to has. So say this has 3, right? But if we're going to use this nabla on this function, which one has 2 variables, it becomes only 2. So only have these 2. So your nabla of f, this is just going to give you dot this, right? d dx dot your f. So basically just d dx of f plus your df dy. And this is going to be your divergence. Divergence, you see, this is a scalar quantity, right? This is a vector function, but this is a scalar function. And now the next topic we're going to be doing is curl. And curl is basically, how do you explain it? It's basically like how something rotates, right, from the name. So it's kind of hard. So think about like you have a vector field that goes this way. And think about you have a stick. And how the water will push the stick around, because if it's like going this way, right, it'll apply torque this way and this way, so you think the stick will twirl this way, right? And that's the curl. So basically how you calculate the curl is a bit more complicated than the divergence. So curl is basically just, let's go to some empty space. It's just a nabla symbol cross your function. So for this case, I'll just use a 3D example to make it more general, because most times you're doing it in 3D. So say you have a function f with 3 variables. Well, apply this, right? So this is going to be equal to, you know, the cross product algebraically from your vector classes, right? Let's write the, so it's going to be partial x, partial y, partial z. So this is your matrix for cross product to make it easier. And this is your f in the x part, and f in the y part, and f in the z part. Right, this is your matrix. So you know the first part, you're going to take the x direction, right? So this is going to be x direction. And now you're going to do this cross, this times this. So partial fz, partial y, plus this and this. So partial fy, partial z. Right? The next part, you're going to get plus the y direction. Now this here, you're going to have partial z and partial x, right? So partial fx, partial z, plus opposite way, partial fz, partial x. Wait, I made a mistake. It's supposed to be plus and minus, right? So plus and minus. So this actually should be a negative sign here. Should be plus and minus. And womp. Right. Yes, I'm using this pen. All right, so this will be minus and minus. Right, now for the last one, in the z direction. Right. So for z direction, it's going to be this column is this, right? So it's going to be partial fy, partial x, minus partial fx, partial y. And this is basically your function. This is basically your formula for the curl. And notice curl is actually not a scalar, it's a vector because it has 3 parts. So it's actually a vector. And that's going to be it for today's lesson.